Now I'm going to continue and I'm going to discuss inverse kinematics of six-axis robots. And this portion of the lecture, you're not really responsible for it. All right, but I want to go over it just to give you an idea for those of you who want to further pursue their education into robotics, robotic research, or any type of manipulation. I think you will find this very valuable. So the six-axis robot will essentially allow you to control the position of the end effector and also the orientation. So let me actually first draw how the six-axis robot actually look like. It turned out that it actually is a combination of the two that we went over, right? A three-stage robot, right? And then the list robot. So the first stage basically is used to simply locate the position of the end effector. So let me actually draw that for you guys. So this is my first joint, right? Then what I'll actually have is we're gonna have, okay, we're gonna have another joint like that. And this is basically very similar to what I just was explaining. And let me actually do this like that. So here, so this is my three-stage robot, right? Basically, we have here, you know, um, x0, we have y0, and then we have, this is my z0, right? And then this guy is my z1, and this guy is my z2. And if I want to place x1, what would x1 look like? X1 is going to be perpendicular to both, right? Z1 and Z0, right? So this guy is going to be my x1. And if I do the mapping over here, which is that, and this guy is going to be here my theta 1, right? Is the angle between x0 and x1, all right? Then theta 2 is the angle between what, x1 and x2. And we know x2 has to be perpendicular to both z2 and z1. So this guy is my x2, right? So that guy, that is my theta 2. So initially, basically, that is really all that I need, right? This guy is my end effector, right? Which has basically now xe, ye, ze. Based on what we just described earlier, we have solutions for theta 1, theta 2, and theta 3, right? And we said initially, obviously, you begin by obtaining theta 3, and then you find theta 2, right? After you've done that based on this length. All right, now let's look into six axes, right? Six axes will actually allow you to control the orientation of the robot or the orientation of the end effector. Here, simply we are positioning this point. It's like, we don't even, we have no control exactly over how this guy would actually look like. There's only a single solution that would actually provide that. Or in other words, there's actually two solutions, right? Elbow down and elbow up. But I actually have no control over, if I actually, if the robot is actually holding this pen, I'm locked into this position, right? Or that position, right? Which is the elbow up position. But what if I would actually like this guy to be exactly parallel, right? Or this guy is like perpendicular, right? If I want to do like a welding operation, how can I actually do that? So then what we do, we actually incorporate another three motors, right? And then those three motors are called the wrist. And this is exactly what we did before. You remember how the wrist looked like, right? So here, essentially, I'm simply putting a wrist on this guy, and then the wrist will actually allow me to control the orientation. So what I'll do here basically is this guy will actually, so the wrist will actually begin here, right? And and it looks like that basically. So this guy will be able to now rotate around itself, right? So this is one motor, and then I actually have one guy is here. So remember, this is exactly like the wrist that we did last time, right? And then this is, I'm gonna have one last motor here. And now basically this guy is my end effector, right? And if I do this, now I'm actually able, if I have a part here, if I have a pen here, I'm actually able to position this pen to be like that, right? Or to be vertical or in any configuration, all right? Remember, this guy was the wrist. So last time we're actually looking at that alone, right? Like that, right? And we said if I have a base frame here, I can actually, point this to any direction that I want, right? So this is basically, essentially, it's doing exactly the same thing. Now that I have my HO3, remember, we have our HO3 based on our, geometrical parameters, right? And, you know, since you have basically HO3, right, you actually have this. So basically you can assume like, you are here on the ground. Basically, you always know where this point is or how this vector is with respect to ground. You are then able to actually control the position of the end effector. But what is actually more important about this is the following, right? Let's say I would actually like to point this guy toward this direction, the direction that I have, right? So what you actually have when you are doing your inverse kinematics, right? You will actually specify your H06, right? You guys agree? I think all of you will agree. When you are doing inverse kinematics, you actually know H06, right? H06 is basically, now this is my end effector. This is called TCP, right? Tool center point, right? And this guy now, I know what is, now this guy is actually my XE, YE, and then ZE. Now actually, I know this. This is like, I want to weld at this point. I want to position an object at this point. So my H06 is what, right? So I'm gonna have basically my at the last frame, right? So which is here. Okay, let me draw this well. So this is my here, my X6, right? And this could be my Y6 is like that, and then my Z6 could be here. And doesn't really matter how this is, right? We said we're always free to choose, the end frame that I want, right? When I'm doing inverse kinematics, basically here is I'm specifying my X6 in frame 0, right? So literally I'm telling what I would like the orientation of the end effector to be with respect to the base frame, right? And then Y60, right? And then Z60. So basically I'm providing all of these, right? And remember, you only provide two vectors, right? So usually you present, for example, X6 and then Y6, right? Y6 will actually tell you the roll, like how much you are rolling this object. And if you are providing X6 and Y6, then Z6 is obtained how? By the cross product, right? Then Z60 is actually equal to what? It will be equal to X60 cross Y60, right? So you don't actually specify that. You cannot specify that, right? It will be a cross product here. And what is the last column on this is basically XE, YE, and then ZE, and then remember this guy is 1. So every time that I'm actually doing inverse kinematics on a 6-axis robot, I need to present this guy and this guy and that guy. So here's the trick here, right? This is how we can actually get to solve this. Once you provide that, so you are providing this, right? So basically you are actually providing X60, right? Or it could be Z60 or whatever it is, right? You always specify that frame. If you're actually providing this vector, so the vector that is actually pointing along this last link, right? You also know from the geometry of the robot, this length, right? Usually this guy is actually D6, right? Okay. If you actually know D6, you can actually find this point. How do you find that point? That point is actually this point minus this vector, right? So you can actually always have this point simply based on this and then based on the value here, right? How do you actually obtain that? This is simply nothing but, vector geometry, right? So if I have this vector here, right? Okay, so if I actually have, this is my vector PE, right? Let's call it like that, right? So PE is what? Is XE, YE, ZE. So PE is, the vector from the origin to, the end effector. I can actually find the position of this point, right? So let's actually call this point PC, right? So what is PC? PC is nothing but PC, okay, I'm gonna write it here. So PC is actually equal to what? Is equal to PE, right? Minus D6 multiplied by X6. All right. If you actually do that, now you actually obtain the coordinate of that point, right? So PC is nothing but PE, which you already have, minus D6, right, multiplied by X6. So now actually you have obtained the position of that point. Now that you've actually obtained the position of that point, you can actually, now you're back at the original robot, right? So you can ignore this rotation because, for me to be able to solve that point, all I need is what? I need to know the length of this link, which I already have, right? And I don't really care about the rotation of this guy. So this configuration of the robot is actually called the Stanford configuration because it was invented at Stanford University. And this basically allows us to actually solve the kinematics of 6-axis robots very easily. All right. So yep, you obtain a position of this point. So this point is actually called rest center. wrist center. All right, so this is the center of the wrist, and the wrists have to have this configuration. So now we have that point. We can now come back to what I originally described, basically how you can obtain the inverse kinematics of this guy, right, up to this point. Now you ignore the rotation of this guy because the rotation of this guy will not actually change the position of that point. And now we're good. Okay, now obviously we still have to solve theta 4, theta 5, theta 6. But how do we solve theta 4, theta 5, theta 6? So now, based on H06, which we're already providing that, we are actually obtaining this point, and then we are solving theta 1, theta 2, theta 3. Okay, so now we actually have we have HO3, right? And then we have HO6, right? So what we need is, we need H3, 6. This is the one that we're missing, right? We need to find the angles on 4, 5, and then 6, right? But let me, before I actually put the DH frames here, right? I want to actually show you how we can do this. So we have HO3, right? This guy is HO6. So this guy is given. This guy is known now, right? Based on this relationship, based on obtaining PC, right? And PC will return what? Will simply return XC, YC, and then ZC, right? And then we will use those to find, theta 1, theta 2, theta 3, based on simply the geometry of the robot. So how do I find H36? So here's what we do. So basically, we know HO6 has to be equal to what? Is equal to HO3 multiplied by H36, right? So what is H36? H36 is equal to, so I do the inverse of this guy. So HO3, so inverse of that, multiplied by HO6. So we have all of these. So now we actually we solved basically H36. And it turned out that based on this particular configuration, we can actually find an analytical solution for H36, which will actually give me the same result. So if once you do H36, you will actually end up with this guy right here. What we actually went over last time. So this is okay. So this is what we actually do. So here, this guy should be the 4-6. Right, I've already described that. So if you actually do this, you will see that you will actually be able to obtain theta 5 directly. You will be able to actually find theta 5 based on this entry of this matrix. After that, you have actually solved that, right? So after you obtain this guy, right, you will basically plug it here, and then you can actually solve theta 5, and then you can use these guys to find theta 4. So now you have theta 5. You can divide this guy over this guy, or this guy over this guy, and then you can find theta 4, and then you divide this guy over this guy, and then you can find theta 6. And this is really the inverse kinematics of 6-axis robots. Let me come back and continue by putting the DH frames on this guy, right? So we already have, right, Z0, Z1, Z2. Now I need Z3, right? So we said Z3 is the axis of actuation, right? So this guy is going to be my Z3. How about Z4? Z4 is going to be perpendicular to this guy, right? So this guy is my Z4. How about my Z5? Z5 is here, right? Okay. Now, next step is we need to place the x-axis, right? So we know x3 has to be perpendicular to what? To Z3 and also Z2, right? Okay, so this is my Z2 is here, and it actually has to intersect Z2, right? So where should I put x3 basically? Right, it has to be perpendicular to Z3, and it also have to cross this guy. So this is my x3 right here, right? All right, now how about x4? So x4 has to be perpendicular to both, right? Z4, and it also has to intersect and be perpendicular to both Z4 and Z3. So how do you guys think that would have to be? Right, so if it's perpendicular to both of them, right, so it has to be perpendicular to their plane, right? So we look at the plane that is made out of Z3 and then Z4, and then we know this guy is gonna look like that, right? So this is my X4. How about my X5? Also has to be perpendicular towards Z4 and then Z5, right? So this is my X5. And how about X6? X6 is going to be perpendicular to Z5 and Z6. So the last frame, since there's no actuator here, you're good. You don't actually need to use a DH frame. You can use whatever frame that you want, but obviously you want to be able to represent whatever transformation that you actually have here. Okay, so we already have X5, we have X6, so you would look into this and then you would find whatever homogeneous transformation that you actually have going on here, right? If you want to actually point this in the direction that you want, or if you want to keep it in DH frame, simply you will basically apply another DH frame here and then you can use it. Okay, but this will obviously change here, right? If you were to use a DH frame. Okay, so this X6 here, it doesn't have to be X6 if you are using a DH frame. So you want to look at whatever vector that you were to actually put. I'm not gonna, if you want to actually use a DH frame here, then, so this is your Z5, right? We have your X5. Then I could simply, then my Z6 would be pointing instead of X6, right? So this guy will actually be updated to to Z6, right? But now you understand the concept. So these are the angles. So how about theta 4 basically? How do you think theta 4 is going to look like? So theta 4 is the angle between what and what? Theta 4 is the angle between X4 and X5, right? So this whole thing wraps around it, right? This guy is my theta 4. How about theta 5? No, wait. Theta 4 is the angle between, I'm sorry, X3 and X4, right? So it's that rotation right here. Okay, this is my theta 4. And it's angle between X3 and X4, right? So by how much? So this is that vector here, X4, and then this guy is X3, right? X3 is fixed. X4 is actually rotating, right? Rotated like that. So this is my theta 4, is the mapping of X4 into here. This guy is actually theta 5, right? Theta 5 is the angle between X4 all the way to X5, right? So if theta 5 was 0, right, this guy would be forming a 90 degree in this case. All right. Now, how about theta 6 is the angle between X5 and X6, right? So this guy would be X6, and if this was to be a DH frame, all right? So this is really the inverse kinematics of these guys, but let me spend a minute to actually show you do the inverse kinematics basically on the wrist itself, and then show you, let me come back to my presentation. And this is my presentation. So why is that? Okay. So this is what I've done here. That this is a a more simplistic introduction where we only look into the direction of the vector. But what I solved here basically is a full solution, basically where you actually provide this transformation, and then you can basically control the position and also the orientation of your end effector and also the rolling of the end effector by specifying these three vectors or two of these vectors. Let me actually quickly do that, go over my presentation. So like I said, a 6-axis manipulator is actually a combination of two, right? The first robot is a XYZ robot, right? Which is only a 3 degrees of freedom robot. And then we actually attach to it that wrist, and then the wrist will actually enable me to position and orient the tool of the end effector on the robot, basically in any position that I want. And this is what we actually have. We've already explained and went over all of this. Okay, so what you see here basically is whatever that I explained here, right? So just watch this presentation and then just kind of go through this. But this is what you should actually go over. All right. Let me actually okay, before we get into differential, let's actually do a quick Matlab example on that. And let me actually share my whole screen for us to be able to do that well. Okay. All right. So if you actually look into what is actually happening here on the end effector, right, or the wrist kinematics, right, if I were actually looking into that, what do you think we're doing here if I want to obtain the transformation between this guy and this guy, or basically frame 3, right, to frame 6, or frame 3 to frame 6. Let me actually pull it from here because I think it's cleaner to actually show it to you directly on here. All right. If I were to actually do the rotational transformation or homogeneous transformation between this guy and this guy, what am I actually doing here, right? Let's actually try and then do it here in Matlab. So what I'm actually doing here is that, okay, so we're going to obtain this transformation between, in our case, this guy is going to be what? So what Z0 is actually pointing along this guy is going to be Z3, right? So we're doing the homogeneous transformation between, in our case, frame 3 to basically frame 6, right? In this case is 0 to 3, so it will basically be the same. So what am I doing basically to come from here to here? I'm rotating, right? So you rotate about Z, right? Well, let's actually introduce our variables. So we have sims theta 4, theta 5, and theta 6, right? And what I'm doing is I'm doing simply rotation about Z by theta 4, right? So if I do rotation about Z by theta 4, I might be able to actually show you the video so we can have them all together just to. So initially, I'm rotating about Z by theta 4, right? So I'm doing the transformation from here to here. So you rotate about Z by theta 4, then you're doing what? Then you're translating, right? And you're translating. And I want to show you guys that the actual translation doesn't get incorporated inside the rotational matrix. So you are translating along Z, right? You translate along Z by a distance of 1. Okay, I'm just going to keep it as a unit, but you will see that. Okay, I might as well actually just to prove to you guys that this doesn't. Okay, sims, I'm going to do sims, this guy. So here D1, L2, L3, right? So the length of this guy is L3, right? And then we said that distance here is going to be D6, or it's actually D5. If you actually do the DH table, it doesn't really matter right now. So I'm just putting it as a number, right, or a value. Okay, after you do your DH table, you will be able to tell exactly what this guy is. Okay, so I have these guys defined as symbolic variables. Okay, so what we're doing is we're doing rotational transformation, right? So we're doing a rotation about, right, Z by theta 4, right? So rotation about Z by theta 4. Then I'm translating about what Z by how much? By L3, right? Because this is the origin of my frame 3, right? So you're translating along Z by this guy, which is L3, right? Then what are you doing here? Basically, you are, okay, it's easier to see on this guy, or you can actually see it here, right? So we're basically, right, we're started here, right? We moved Z3 into here, and now we're here, right? What we have to do is basically now put our x. Okay, so when you rotate about Z by theta 4, basically, right, we have basically put x3 into the same direction as x4, right? So now x3 is actually pointing along x4. Now what we have to do is we have Z3 is pointing up, and then Z4 is actually pointing toward in this direction, right? So I have to basically rotate about x by minus 90 degree, right? So that will actually put my Z3 into Z4, right? So this is my Z3, and then this is my Z4, and this is my current x-axis after I have rotated about Z by theta 4. So I'm gonna rotate, right, this guy by minus pi over 2, right? So I'm gonna rotate about x by how much? By minus pi over 2. So remember, we're gonna do sim pi. Okay, sim pi over 2. It's like that. Okay. So now after having rotated about x by minus pi over 2, so now I'm actually at Z4, right? So now I'm at frame 4. Now I want to move into what frame? I want to move into frame 5. So how do I move into frame 5? Basically, we're gonna rotate about Z4, right? So we rotate about Z4 by theta 5. So this is my theta 5, okay? It starts from here to here, right? My X4 is here, my X5 is here, okay? So I'm gonna rotate first by theta 5 and bring X into X5. Then I'm gonna actually rotate this vector into Z5. I will rotate by X5 by pi over 2, all right? So let's do that. So we rotate about Z by how much? So all the rotations about Z, if you notice that, right? By theta 5. Good. Now we're here. We rotate about Z by theta 5. We're here. Now I need to rotate about X by pi over 2 in order for me to bring Z4 into Z5. Okay. So now we rotate about X by sim pi over 2. All right. Okay, now last step is we're basically, so now Z4 is here. Now simply you rotate about Z5. Okay, so now rotate about Z by how much? By theta 6. Okay, if you rotate about Z by theta 6, now we are here. Then we have the translation, right? Then you translate about what? Z, right? You translate along Z by the last distance, which we symbolically define as what? As D5. Okay, now we are here. Okay, and I want to stop here. Basically, I'm going to assume that Z6 is in the same direction as Z5. Okay, and that will actually do it. So basically, it's like that frame now is here, and it's a proper DH frame. Okay, if I do this, clicking enter here, you will see that. All right. So you see that the geometrical parameters of this, they don't actually show up in your rotational part. So this is my, this is my rotation matrix is here, right? This is the first column, right? So we know we don't need that. Second column is here, this guy, these three, right? Let me see if I can annotate that. Okay, this is a, okay. Oops, oh shit. Okay, undo. Okay, that's fine. Okay, so this is the last part, right? This is the last column, and I know this is going to be the position of my wrist with respect to that frame, right? That's not with respect to the home frame, but I don't need that. Basically, all that I'm interested is in actually, after that I solve H36, right? I'm going to actually compare it to this guy, right? And I want to see if I can actually solve theta 5, and in reality, I can, right? So that's it. So you can actually solve after you do this operation, you can actually obtain from this guy, you can look at the entry that this guy will actually return for you. And then you can use this to actually find theta 5. Once you have theta 5, you can solve theta 4 based on these two. So you can look into that. And then this guy, divide them into each other, and you can find the tangent of them. And then theta 6, you look into this guy and then this guy. You notice that the first 2 by 2 in the H transformation, you actually need that, right? You just need this guy and this guy, right? You need the third. You need the first 3 entry of the third row, and then you need the first 3 entry of the third column, right? And you will actually use just that. So if I actually look into H36, right? So I don't really care about these guys, right? I just need this value, and then this value, right? And we don't actually need none of the rest, right? To look into, to find theta 4, theta 4, theta 5, and then theta 6. So you find theta 5 from this guy, right? Theta 5. And then you find theta 4 from this guy. And then you find theta 6 from this guy. Okay, so just put some X here. So this is what we actually want. Okay. All right, guys. So that is it regarding the kinematics of 6-axis robots. All right. And you're not really responsible for doing all this, right? But you are responsible for 2 degrees of freedom systems, right? Just understanding 2 degrees of freedom system, understanding all how we do the homogeneous transformations, understanding all that stuff. All right. Okay, guys. Any questions on that? Just let me know, and I'd be very happy to help you out. All right. Thank you.